Okay, so now the meeting is being recorded. Okay, so in case you want to hide your face or anything, if at any time you have questions, just you can chat or just unmute yourself and shout out. Uh, and so here, so this is a really basic. Okay, assignment. So oh, import. I don't want that there. Okay, I still don't want that there. Okay, okay. So Okay, so let's just talk about the assignment. There's the student class and a my student class. A lot of it is, there's nothing super exciting about maybe some of the features, but there's something that's, a little bit different than, yeah, there's an animal with me. Okay, so let's just open up the assignment, and then I have this main method that you're going to use. Okay, so yeah, so there's a lot of this stuff we learned right at the end of the last semester. Those of you who had me, and what's new is maybe this last bullet item. Yeah, we talked about this the other day. Multiple constructors and using this to call a constructor in the same class, and then and what we talked about last year. And I can't really should have reviewed a little. Quiet. Then and then yeah, that wasn't. I wasn't talking about the class. I'm talking talking to my friend who's crawling on the floor. Okay, so using the keyword super to evoke a constructor in the parent class, I do have an example of that. So the one thing about constructors is that every constructor either calls is either calling invoking a constructor in the parent class via super or invoking a constructor in the same class via this. And it's always so either we're calling a constructor in the same class with this. It's always the first statement. Remember, that's one of the things we talked about the other way, that this, when we call one constructor can call another constructor in the same class with the keyword this, it's this left paren. Do I think, yeah, we can do that a little bit. Yeah, let's do that as maybe at the end of the class, or I can do it after what I'm talking about right now. Okay. Okay. So, yeah, we'll talk about the compare just for a few minutes, and then hopefully I can answer your question. I'll give you a suggestion, but I think if you're having a trouble with the compare, I'm not sure it'll help. I give it to another student, so we'll see. Okay. Okay, so where were they? Okay, so constructors either call a constructor in the same class or call a constructor in the parent class. If we do not explicitly call a constructor in the parent class, the compiler will just put super empty set of parentheses in. Okay, so in this class, you're going to be calling a constructor in the same class, a constructor in the parent class. You write a toString and an equals, real basic stuff. And I do have an example. There's like an example at this person in my person class. So just look at that. And it's for, we can look at that as well. Okay, but it's this thing right here: protect data stored in the instance variables. This is what I want to talk about. And a lot of students, kind of skip this part. So here's page 2 of the assignment. And I know I given similar assignments, or maybe even the same assignment before, and this page gets skipped a lot. Okay, so read this page 2. Every word I write is totally fascinating, so don't skip anything. And this is what. So this is. I think if I taught math 130, if I was teaching math 130, I might actually do this. Isn't this that's the kind of the typical way of. We have one of the instance variables is. Here are the instance variables for the student class. We have a private instance variable like private string first name, private string last name, private int grade. So grades would be like grades for an exam or whatever. And typically, what do we tell you in math 130? Oh, just go this dot grades is assigned grades. What grades would be on the right side would be the parameter, and on the left side would be the instance variable. What I'm saying, they can generate errors because it says because okay, where is grades? I'm talking about this grades on the right side. That's the parameter, and it's getting an address from the main method, right? So when we create so typically when we create an object, it's created in the main method, and and then the main method would go like new student to put a first name in, the last name in, an array of grades. Okay, so the right side is an address, and it's an address where they're for an array in the main method. And on the left side is this dot grades, which is the instance variable, and they both have the same address. That's the problem. Where an instance variable where an instance variable and a variable in the main method refer to the exact same array. So if the main method changes the array, oh, the object is changed. So I shouldn't be able to change an object by changing an array element. Okay, and vice versa. I shouldn't be able to change data in the main method by changing an instance variable. So I actually do have an example here of what I'm talking about. And it's pretty clear what has to be done. You know, if you read this, all I'm saying is like in the set grades method or in the constructor, you just go you just create an array of length grades. So it's so now this dot grades points to a totally new array, and you just use system array copy to copy the data and the parameter to this dot grades. So it's 2 lines. Okay, and if you do that, then this dot grades has a unique address. It's not the same address as an address in the main method. Now let's see if I can, okay, let's see if I can, okay, so here, I have this really great example here. Okay, so I did this in the last class. Does everyone see Eclipse? Are you seeing Eclipse right now?
Yeah.
Okay, so now, so it's really kind of a silly example. Okay, and the whole point was to demonstrate that this whole concept of, okay, so we start in the main method. Actually, I put the main method in the same as the class, which is, you can do that. Right? Okay, so I can write a static method anywhere. So if you look at line 18, I create a local integer. So that's the main method. And we create a local integer array, I call it X, and we initialize it to 9, 8, and 17. And then I create an example object, right? So if you look at my class on line 6, that's my constructor. And right, the constructor expects an address that refers to a list of integers. And notice what we're doing. So line 7 is doing what I'm asking us not to do. This dot numbers is assigned number. So what's happening there is that line 18, the address of X and the address of this dot numbers is identical. Right, so yeah, so if you look at my comment there on line 21, variable X in main and this dot numbers in the example object store the same address. Right, so go ahead.
So I know you're explaining why it's bad, but so on line 6 and 7, you said to do a system array copy. So
Right.
So after you do the this dot numbers and the new int, like if you were doing it properly, after that line, you would do system array dot copy numbers.
Well, what I would do, I wouldn't have that line 7 at all. So line 7, what you would do is you would allocate memory. Instead of going this dot numbers as assigned numbers, you allocate memory. You go like this dot grades is new int, and you know, and then you put the length of the input parameter, which is also called numbers.
So then where does the system array copy?
And after you allocate memory, then you do the system array copy. So it's 2 lines instead of 1.
So it would be system array copy grades?
So no, well in this case, yeah, you copy the parameter to the, see, they both have the same names, you gotta be careful. So you copy the parameter grades to the instance variable grades. So the parameter is the source, like grades is the source, the parameter grades is the source, and this dot grades is the target. So grades would be first, and this dot grades would be the third argument.
Okay. Helpful? Yes, sir. Thank you.
Okay. So let's just show. So I'm saying line 7, bad, very bad, very bad. Yeah. So I did. Yeah. So if you're taking notes, very bad. Okay. Don't let this happen to you. Basically. Okay. So okay. So let's just run this really interesting example. Okay. So so look at there at line 23. X of 0 is 9. And then I'm going to call increase position 0. Yeah, so basically what I'm doing is I mean, maybe it's not a great method. So line 24 goes, you know, we invoke the method defined in line 10, and we're increasing numbers of 0. We're going number 0 plus plus. We're incrementing it by 1. But what I'm saying is when the instance variable gets increased by 1, the data in the main method also gets increased by 1. So changing numbers there on line 14, changing that instance variable should not change this original data at all, and vice versa. So let's just see here. Let's just run this code here. Oh, why is this so slow? Yeah, I might have an error in one of my files. So it's yeah, that has to do with a different file. We can run this. Okay, so x of 0 was initialized to 9, and then what happens? It becomes 10 after calling increase position 0. See, we don't want that. There's no way that this object ex, the object ex should only be able to change its instance variables. It shouldn't be able to change this array in line 18. We passed the date. We initialized numbers with that data, but the only thing that and this object there in line 20, we're calling it ex. Ex should only be able to change its instance variables, and that array on line 18 is not an instance variable. So it's an unintended side effect. It's bad. Well, how about this? Now here's another one I did do in my other class, and then so let's say I go x of 2. I think this should work. I'm going x of 2 is assigned, I don't know, let's say 100. Why is okay? And now what I want to do is, okay, let's say I go, I have another method here. We'll call it display numbers. And let's just have this loop right here. For x in numbers, oh no, I want the, sorry, so I want to use the other kind of loop. Okay, I want an index. Okay, for int I is 0, I less than. Okay, so then system.out. Okay, and then let's see, plus, sorry, it's numbers. Sorry, I'm not paying attention, students. Numbers, and then plus, all right. What doesn't like something I did there? Oh. Okay, so now let's see what happens. So we're gonna call display numbers ex.display numbers. Let's call it again. Then we're gonna first. Oh, what did I just do? Darn it. Sorry, students. And then we're going to call it again. So the first time we should see numbers of 2 should be 17, and then in the main method I go x of 2 is 100, and I think we're going to see 100. Yeah, do you see that? It's a little bit of a mess there. Here, maybe I can do a little bit of a better job. So I will, but I think you can see this. So let's get rid of this. Let's get rid of this. Okay, so let's just run it one more time. And the first time we're going to see 9, 8, 17, and then we're going to see 9, 8, 100. See 9, 8, 17. That's the original data that was in the array. Oh, then now numbers of 2 is 100. Now let's go back to our code. See what happens? In the main method, I want x of 2 is 100. So this changes the instance variable numbers, right? I shouldn't be able to do that, right? The only way I should change numbers, that instance variable, is by but it's only, the only way I should do this is with that variable, with this example object ex. I shouldn't just be changing, like a local variable should not have access to the instance variables in an object, right? It's only the object itself should have access to the instance variables, right? And furthermore, an object, like that object ex we define in line 20 seconds, shouldn't be able to change a local variable in the main method. But in this case, we have this bad side effect. It's all because of this line 7. It's all because we're assigning an address. We're taking an address that was, we're taking an address that was created there on line 24, and we're assigning it to the instance variable numbers. So that's what we want to avoid. That's the whole point of what I'm talking about there. Instead, allocate memory. Allocate memory for the numbers array. You have a totally new array. You have a new address. And now just do a system array copy. So, all right. So why don't you try that? If you have questions, you can just email me your code. I think you'll learn something from doing this. One thing to do is just to write your set grades method. Do this in the set grades method, and then the constructor can just call set grades. And then you don't have to repeat the code repeat the code. And then you do something similar for the get grades. You create a new array, and then and I tell you what to do. When you allocate memory for a new array, copy the instance variable into this new array, and then you return it. But it's all there on that second page of the assignment. So and then if you have questions about like the instance, if you have questions about like just look at that example I gave, the person in the toString, and it should have everything. There's an example there, but don't hesitate to ask questions. But any questions right now? I'd like to
Yeah.
talk. Go ahead, Marcos.
I was just gonna ask after you do your lecture if you can just tell me if I'm in the right direction. I've already been working on the homework, so I was just wondering if after class you could maybe do some pointers, because I'm kind of confused on some stuff. So if that's okay.
Tell you what, can you mail it to me?
Yeah, I'll email it to you.
Yeah, email it to me, and when I'm done, I can just we can do it that way. If you want to get on Zoom and talk about it too, yeah, but definitely emailing it to me would really be a big help.
Okay, thank you.
Okay, so let me see if I can answer Kyle's question a little bit. Okay, so let's look at, there's that book class, and let me just let's see if I can do the book problem. And this is
Okay, I was a little.
what's
Sorry,
your
I was a
question?
little. Sorry, I was still a little confused on the compare to method on the purpose from it, because I thought.
Purpose.
Uh,
Okay, go ahead.
sorry, I
It's a
thought.
little contrived. See, the thing is,
Hmm.
because we cannot go here. Let me see if I can do. Do you mind if I just wipe all this code out right here? Or I can do a new one here. Let me just. I'm just gonna turn to a comment in case anyone's dying to see this. Okay, let's just see this. Okay, so let's say I go like this. Okay, Boolean flag. Okay, so remember that's going to be true or false. And then let's say I want to know, is 2 greater than 1? So I go 2 greater than 1. Remember the greater thans and the less thans, they create Boolean expressions. Remember, you always start on the right side here. I'll even put it in parentheses, even though it's not required. See what's in the parentheses? Why does it? Oh, okay. What's in the parentheses is either true, 2 is greater than 1, or it's not greater than 1. There's just, it's only 2 options, true or false. And we assign it to that Boolean variable flag. So here we're comparing int values with something that we're familiar with before Math 130 or Math 1, like we learned in all our regular, I don't know, when do you learn that about the greater than sign? I don't know when they introduced it, but a long time. We've probably all been using it for like, a super long time. It's like our best friend. Yeah, it's always there. The greater than operator is very loyal. Okay, so okay, but now let's try to do that with strings. Oh, Boolean flag 2. Let's say I want to know, is cat greater than dog? And remember, for one string to be bigger than another means the one that's the word. So it's like the dictionary. The word that's further back is the is considered to be the larger word. Okay, so let's say I go cat greater than dog. Now, actually, if we're doing dictionary ordering, dog comes after cats. This would actually be false, but we're going to get a compiler error. Whoops, I'm missing a parenthesis. Okay, so I don't need the parentheses in line 25 or 27. I'm just doing it for emphasis. And what does the compiler error say? It says the operator greater than is undefined for strings. Basically, that's what it's saying. It's pretty wordy. The operator is undefined for the argument types java.lang.string, comma java.lang.string, meaning we cannot compare. So if you want to, so if the compare to takes I'm really glad you asked this question. I probably should have. I know when I'm in class, sometimes I write more on the board, and I'm not really, doing that here. Okay, so let me just show you something though. Okay, so for objects, okay. So we have to compare objects with them via methods. That's where the compare to comes in. Okay, so if I want to know cat, and I'll put this in let me just create a comment here. Cat greater than dog. Okay, so that's meaningless, right? And so the whole, remember, we're gonna, one of the things we want to do in this course is learn algorithms, how to sort. Well, to sort to sort two things, you have to order them, like which one's bigger, which one's smaller. So you have to be able to compare, like prices. We're going to order by price. Well, which is the bigger price? Okay, so we want to compare strings. So is equivalent in Java. So we cannot use greater than. The compiler is just going to give you a red dot and, is equivalent to cat dot compare to dog greater than 0. So, whoops, we have to compare, whoops, and let me just close off that comment. Right, so if I want to, I'll put, that's wrong, that's right, okay. So if we want to compare two strings, we actually have to use what's there. Can you see that line 34? That's what you have to use. You have to use this compare to method, right? And so cat greater than dog, if we want to see, if we wanted to see if cat's greater than dog, that's the correct way to write it. Cat dot compare to dog. And then there's this rule that was created long before, I don't know, probably it's been there for 20 years. So, whoever developed Java said, okay, this is kind of what I have in the notes online, that obj1 dot compare to obj2. This is kind of just a made up rule. Greater than 0 means obj1 is greater than obj2. And the other way around, if obj1 dot compare to, the compare to method returns a negative, then obj1 is less than obj2. Yeah, so that's what the compare to does. So we have to make sure, so we decide what it means for one object to be bigger than another, right? So we decide what it means for one object, but we have to make sure our compare to, we either, the correct, just returns positive at the correct place, returns positive or negative. And if the objects are equal, it should return 0. Am I helping? Is this helping a little bit, Kyle?
Yeah, I already understand it way better than I did before.
Okay.
Because on the test, I kind of just answered the questions according to the practice questions. So
Okay.
it feels like I kind of rewrote it according to the test question.
Okay.
But I didn't really fully understand it till now.
Okay, it's kind of subtle. I'm glad you asked. It's actually kind of subtle. The whole like why compare it to 0, because that's what they're telling us to do. Someone just came up with that rule and said that's what we're going to do. That's how we're going to compare objects with the compare to method. So, and that's why if we're like, let me just show you like in that book. Let me just do the book class really fast, and then we'll get on to the main event if that's okay. Okay, so let's just. I'm going to. And I think in the book I said, I think that the author with the fewer characters in the last name or the name is actually the larger, considered to be the larger book object. So it's kind of a funny, way of ordering, but as I'm saying, you can do, I'll put a main method in here. Okay, so we don't need that. Okay, so private, I can't remember, was it string, title? This should only take a minute. Private string, author, like author's name. And then let's see here. Go source, generate. And see, what Eclipse does it. See how line 10, I had it generate the constructor. And see how that super empty set of parentheses, this is actually calls the constructor in the object class. The object class has a constructor with no parameters, but that's what that is. It's really unnecessary, but I'll leave it there. Okay. And then and then we have this compare to method, public, and I said, okay, so public int compare to, then let's say call it B. Okay, so then, and I want, okay, so return, okay, so it's the short, so B dot author dot length, because the author is a string, so it's a length property. So this dot author dot length. Okay, so that's a difference, right? So it's a number. We're subtracting two integers, right? Length returns an integer, and so when is that going to be positive? It's positive. So it's, remember, if you subtract a smaller number from a larger number, you get a positive, like 7 minus 6 is positive. So positive when, so it's when this dot author dot length is less than B dot author dot. Did I spell that right? All right. So, and this always corresponds to the calling object. It's always like when I'm knowing all these examples, I'm going obj1 dot compared to obj2. B is the input parameter, and this is always the calling object. So let's see here. So let's just kind of make up some names here. Okay, so book, and so BK1 new book, and I'll put biology, and then how about ESS? Yeah, okay. That's a short last name, right? And then book BK2. Oh, what am I doing here? Okay, new book. And how about I like Java, and by, I don't know, Monday. Okay, so book 2, the author is 6 characters. Book 1, the author is 3. So according to the comparison, now let's do this. So let's see. Let's just print out. Okay. Let's just print out. Okay, so let's just print out the result of the compare to method. System.out.println bk1 dot compare to bk2, right? So in this case, okay, so bk1 is the equivalent of this, right? In the compare to, and bk2 is the input parameter. So it's equivalent to the b variable, the input parameter. And we should get 6 minus 3. 6, I'm not sure what that means. Some people are doing those like.
I was confused on this too, so I'm glad you're going over it.
Okay, so now why am I getting because I don't have a comment here. So that's what I'm saying. If you can always try substitute, just substitute the values and let's go back to the original method. Shouldn't we get, it should be, okay, so BK is B, right? And the length of Monday is 6. The author is Monday, right? And the length is 6. And BK1, the author is S, and the length is 3. And what are we returning? B.author.length minus this .author.length. And we should get 3 in return. So let's see here, which would mean that, so BK1 would actually be, see, it's 3. So what does that mean? It means that, oh, it's returning a positive value.
So when we're comparing two different objects, when we're calling the method to compare it, if the second input is greater, then it's true.
Say it again. I'm not sure.
When we're calling the compare to method,
Right.
if the second input that we put into it is larger, then it's true.
Okay, it's true if the method returns a positive value. I'm not sure I'm answering your question. Okay, so
I'm saying since the first of the second object we're putting in actually
for this
BK2,
particular, okay, for this particular, okay, for the book class, the longer the last name, yes, if the input argument has a longer last name, yes, we're going to get then BK then BK1 is, let me call this object 1 and object 2. Let's just go. Yeah, so object 1, so the calling object, that's the one that, it's always the one to the left of the period. That's the calling object. That's always the this. And the input parameter is always the obj2 is the input parameter. Okay, so in this case, we're going to get a positive value, right? Compared to, see, object 1 dot compared to obj2 is positive. Okay, so positive. So obj1 is considered to be greater than obj2. And now let's create a third like object here. Maybe how about book obj3 is a new book. Okay, let's just call it, I don't know, algebra. We like algebra. And how about I don't know, how about no, something like AA. That'll be a very unusual last name. Okay, so remember the short, okay, so now what I'm going to do is, okay, so now let's try this, okay? Let's compare obj3, the length of the calling object, let's put obj1 in here. Is that right? I want to do, okay. So that has length 2. Yeah, so that's like, okay, let me do this. obj2, let's see, which one? So that's Monday into, so okay, so obj2 here, let's just put obj, obj2. obj2 is the one with 6, and that's the one that's being subtracted. And how about obj3 here? Is that right? The one, no, I think that's, the one with the shorter last name is, okay, so let's put 2 here. Sorry, I'm getting confusing this. Okay. So obj3 has a, oh, I keep it, sorry. obj3, that's right. Okay. Okay, so obj2, and it should be the input parameter, and it should be, in this case, the length of the last name equals 2, right? obj3 here, the length is 2. And here, and then the last name equals 6. So, okay, so in this case, okay, so obj2 is the calling object, and it actually has a longer last name than the input parameter, which is obj3. And so it should return, what is it? It should return 2 minus obj2, 6. It should return -4, which would mean that obj2 is, when it returns a negative value, yeah, you get a negative value. Okay, so in this case, obj2 is less than the input argument, obj3. Okay, so I got a little confused. I was writing the example, so maybe that confused us. Okay, so here is that we need the, let me just summarize. We need the comparative to compare objects, because we can, like our own person, and we can compare any two objects in the world, but we have to do it via a compare to method, and we have to write the compare to method, and we make up the rules for the, what does it mean for one object to be bigger than another. So I'm saying for this book class, the shorter the last name of the author, the bigger the object. So I want to make sure that if I put in, so if I go, if obj1 dot compared to obj2 is positive, so if obj, so if the, let me, I have someone saying something to me. Okay, no, so that's the rule. Okay, so the rule is if compared to, right, so in this case, okay, so in this case, it returns it prints a negative number, right, for the last one? Remember, the rule is, that's the rule we have, right? OBJ, so let me just not call them OBJs anymore. So A dot compared to B greater than 0 means A is greater than B. A dot compared to less than 0 means A is less than B. Oh, sorry. So if it returns it, so if the compare to returns a positive value, then the calling object is bigger than the input parameter. If compare to returns a negative value, then the calling object is less than the input parameter. I'm having a hard time seeing this chat. Okay. That's it. Okay. Yeah, so we're checking if the parameter. It doesn't really, oh, Kyle, it doesn't matter. Your question, it doesn't matter.
Oh, okay. That answers my main question that I've been wondering like for the past couple of days.
Okay. Yeah, so in this case, but look at that compared to. When would that expression return a positive value? When the last name of B is greater than last, so this is positive. When last name of B is greater than the last name of this. Right? So when the calling object has a smaller last name, we get a positive value. Is this how I feel like I'm making it worse by talking so much? Why don't I let you think about it and I'll stop talking?
That was good. Thank you.
Okay, so I'm going
Yeah,
to.
I understand it now too.
Okay, but write me if you still have questions about it. I think I've said I might have some more notes about this, and I'll put up. You know what? I'm going to put up a chart. I think I remember years past. I put up a chart, kind of like what I did before, about just explains the equivalence of greater than for an int and compared to for an object. So I'll put up a chart like that as well. Maybe that'll help. So what I'd like to do now, I think I'd like to stop the recording and then restart it again. So, because it's getting kind of long, and that way I want to talk about, so that way someone doesn't have to go all the way through to the, well, you know what, maybe I won't do that. I'll just tell them what minute this starts in case people just want to scroll to this new topic. Okay, so so we're going to talk about, so I'm going to just, I don't need this anymore. I want to talk about, this is probably the most theoretical part of the course I'm going to talk about right now. And so I have these files here. I haven't created a module yet. So this is just kind of an introduction to this topic of order of growth. And what one of the things you do, especially if, let's say you went out in computer science and maybe you went got a master's degree or did a little more theoretical research, but you talk about a rough idea of the runtime of an algorithm. How many floating point operations does it take to complete the algorithm? And we should be a little familiar with the terminology. So it's kind of a dry lecture. There's probably the most math that you're going to see in this whole course is about what I'm going to do right now. It's not really a lot. So let me just look at this. And then we're going to look at, let's just go through the lecture. And the problems really are not too bad. So some of the problems will be on the next quiz, along with writing a constructor that calls another constructor in the same class. So I'll put the announcement up tonight. Okay, so let me just do the lecture from here, and I do the worksheet I'll open up the files on my computer. Okay, so this is a chapter, yeah, so lecture files, this is lecture 7, okay, order growth. So this will take 20 or 25 minutes, and just remember, students, if you have something you need to do, it doesn't hurt my feelings if you're not here. Okay, so okay, so analysis of algorithm, and I take this material from a book called Sedgwick. If you can just if you want to go to Google right now, you just type in Sedgwick blank algorithms, and yeah, and there's that guy's name, Sedgwick. He's very famous, and everything you need to know from his book is online for free. Okay, so it's hard to read, but I try to, I like the one thing I like about his website, he has all the codes at his website. And so it kind of, he implements all the algorithms, where like some books, they don't actually implement algorithms, they just use pseudocode, which is almost impossible to read. So let's just start with that example there. And let's say we have 2 arrays, each of the same size, or maybe you've done this, you've taken a physics class or linear algebra class, and you've talked about the inner product of 2 vectors, inner product of 2 vectors. You can think of a vector as just like an array. It's just a sequence of numbers with a subscript. Okay, so let's say I have this array. Now I'm starting to count the index by 1 instead of by 0. And what we're going to do is we're going to multiply component-wise and add all the numbers together. Let's get how many operations would this take? Okay, well, there's n multiplications, right? N numbers in A, n numbers in B. We multiply A1 times B1, add it to A2 times B2, and so forth. And you see what we have there is yeah, so there's n multiplications and n multiplications and n minus 1 additions, and you sum that together, and it's all together. So to do that inner product that I have right here takes 2n minus 1 additions. Okay, let's say our data size is large, or n is large. This is the thing about computer scientists, they just throw away numbers. Okay, so we only care about the highest order term, which is 2n, right? You even do that in your algebra class when you're talking about limits of very large numbers, like as n goes to infinity. You just drop all these lower order terms because they get so small compared to the highest order term. So if you graphed 2n, like when n like 2n, if you when n is like 50,000, 2n is 100,000. So take away 1. Like if you have $100,000 and you lose $1, you probably won't be crushed. But if you have like $3 and you lose $1, you might feel bad. Okay, so so I'm saying, so when 2n minus 1, the minus 1 is not big for very large n. So these problems, I'm thinking about super large n, not tiny numbers, large numbers. So all we care about is that factor, that term 2n. And eventually what we do is we just drop that 2. All we really care about is n. We care what is the highest order, what's the highest order term in there, and that's order n, degree n. Okay, so I can even take this out of the slides. It's in Sedgwick's book. He does talk about this thing called a tilde operator, and I used to ask the students to do it, and I go, and I'm being just silly. Okay, but it's there. Okay, so that symbol there is a tilde, and so like for our algorithm we just did, it's tilde 2n. So here's actually the definition of tilde. So, okay, so like g of n is tilde f of n if their quotient goes to 1 as n goes to infinity. So basically, so if you have these two functions, and for a very large n, they're essentially like you graphed them, and the graphs look almost identical, then you would say g of n is tilde f of n. And I don't care. I mean, students, you can just forget this as fast as I'm saying it. If you only if you want, okay, it's not something that we're going to be talking about anymore a lot. Okay, and so yeah, so like this limit to what I said is 2n. So remember the number of operations for that inner product. Remember this that array that we're adding together. Those two arrays we're multiplying component wise and then adding. We're saying that's 2n minus 1 operations. And I'm saying, oh, let's just throw away the 1. The negative 1. It doesn't really matter. And so what I see here, the limit of 2n minus 1 over 2 of n it's 1 as n goes to infinity. Like put a really the larger the n, the closer you're going to get to 1. Okay, so and it doesn't take long before you get to 1. Like even if n is like if n is 10, it's 19 over 20. It's almost 1 right there. So okay, but the term that we really care about is order of growth. And we want to just know the degree of the highest order term. Okay, so in this case, what all we care about is the n. We don't care about the coefficient of 2. So remember the actual number of operations for that inner product, or multiplying two arrays component-wise and then adding the terms, is 2n minus 1. Then, okay, so then we go, well, who cares about that minus 1? Let's just toss it away. If n is big, who cares? And then there's this expression order of growth. We get rid of the coefficient. Okay, we say grows like n. N would mean linear. N to the first, it's linear. Meaning if you double the data size, you roughly double the number of operations. So if n is like 100, we're doing roughly 200 operations. But let's say we go from 100 to 200. Now we're going from, the number of operations doubles, right? You double n, the number of operations doubles. So when the order of growth is n, that's why we care about the order of growth. What's the rate of increase in the number of operations if we double the data size? So that's all so that's kind of what I'm thinking about. So if I go from 100, let's say if I go from 50, n is 50, it's 100 operations. You double the 50 to 100, oh, now it's 200 operations. So double the data size, double the number of operations. And that's great. That's like one of our best case scenarios. We like, most of our algorithms are going to be what is called n log n. Where the log is typically base 2, but we really don't care about the base so much. Okay, so so here's this kind of definition of, or I don't care if you know the definition of order growth. Okay, what it would say is g of n, the order of growth of the order of growth of f of n, the order of growth of f of n is g of n if g of n is tilde a times f of n. Basically, all that means is the quotient of g of n divided by f of n approaches some positive constant a as n goes to infinity. So for super large n, one is just a multiple of the other. Okay, and that's all that would mean, right? So let's go back here. So if you look here, so 2n minus 1 is about double n, right? So for very large n, 2n minus 1 is about twice n. So that's all so basically we're saying is two functions are, the order of growth of 2n minus 1 is n because we can, for very large n, n is a multiple of 2n minus 1. The functions behave very similarly for large n by if you multiply by a constant. And that's all that means. So and again, I'm saying this is kind of theoretical. And if you don't like math, don't worry about it too much. Or you have to like math. If you want to, I guess you have to take physics and calculus. Okay. Doesn't mean you have to like math though, if you have to take it. Okay. So anyway, so students, actually finding the order of growth really isn't, for the problems I have here, are really not too bad. So here are some contrived problems. Then we'll look at the worksheet. So let's say, and this is kind of made up because it's unlikely. Let's say we have some algorithm while we're sorting or we're doing something, and let's say we count the actual number of operations. Let's say the data size is, let n represent the data size. So let's say like n is 1,000,000 integers. Okay, and we're doing something to these 1,000,000 integers, and the number of operations, like the number of like additions and multiplications. If we added up all the additions and multiplications and subtractions, and like how many operations would it take to complete this algorithm? Like how long would it take to sort all these numbers? Let's say it's n cubed over 6 minus n squared over 2 plus n over 3. And that's totally contrived and made up. It's what I'm saying is that the order of growth, all you have to do is look at the highest order term, which is n cubed, right? N cubed, you look at in this case, 3 is the highest exponent. For a large n cubed grows much faster than n squared. Like, let's say n is 1,000,000, like 1,000,000 cubed is a lot bigger than 1,000,000 squared, right? Because 1,000,000, what is it? 1,000,000 is 10 to the 6, right? Right? So basically it's saying 10, so 1,000,000 cubed is 10 to the 18th, and 1,000,000 squared is 10 to the 12th. So you do that like to a trillion, then you're really talking about a huge difference. So for that n cubed over 6 problem, I'm looking at this last slide down here. The dominant term is n cubed. So we're saying the order. Oh, go ahead.
I was just gonna say, so is this like an example, like of example problem you would see on the quiz on Wednesday?
Yeah. I'm going to show you a few.
Okay.
Okay. Yeah. It's all that's all I want you to recognize for right now. And then okay. So yeah. So the highest. So this is the patterns are pretty easy. The concept might be a little bit hard, but the patterns are easy. Okay. So okay. So in this case, the dominant term is, so the runtime of this algorithm behaves like n cubed. That's the dominant term. That's really what's dominating. So if you double n, so 2n cubed is 8. It grows by a factor of 8, right? So cubing is really not good. Like if you like 4 cubed is, what is it, 64? So if you go from okay, so it's really not good. So an n cube algorithm is just, if you double the data size, you're going to get this explosion in the number of floating point operations. So okay. Okay, here's another one. Again, it's a very silly example. Oh, hold on here. Someone's acting very bad. Okay. So let's say the actual number of operations is log of n plus 1. And I'm not putting a base there, because you can go from one base to another just by multiplying by a constant. So usually it's either log 10 or log 2. And in this course, a lot of times it's log 2. And the dominant term is log of n. 1 just stays constant. So for large n, log of n, let's say it's log base 2 and the n is like 2 to 1,000,000. Well, then the log would be 1,000,000. So log of n for large n grows much faster than 1. So the dominant term there is log of n. Yeah, so and again, so the order of growth is log of n. It behaves for large n that algorithm. So if the number of operations, let's say the exact number of operations for some algorithm is log of n plus 1, we say, it grows like log of n. We're going to skip this one, Frank, because I haven't talked about stacks yet. I was going to talk about binary search next time, but I think I'd like to talk about the stacked data structure, which is more fun than this, I think. The stacks would be the most fun we've done so far. So don't you wish it was Wednesday already? Okay, so anyway, okay, I said this, it comes from the book. This Sedgwick book is used at Princeton, by the way. So I think we're just as good as they are, Princeton. Our tuition's a lot lower. Anyway, okay, so here you have this nested loop, and I'm saying, let's get some kind of rough idea of the number of operations, the order of growth. Okay, and what you do, it's a nested loop. So the outer loop, think of it as like an Excel spreadsheet. The outer loop is the number of rows, and the inner loop is the number of columns. And see in the outer loop, see how it's incrementing by 1. It's incrementing by, the important thing is incrementing by a constant. And this inner loop is also incrementing by a constant. So the number of iterations of the outer loop is n. The number of iterations, so the number of rows is n, and the number of columns would be like about n over 2. So for every row, there's about n over 2 columns. So the number of cells altogether is, you just multiply together. See, now the number of operations for every iteration is a constant. This is why this works. Sum plus plus, we're just adding 1 each time. So it's 1 addition for every iteration. So as long as the number of iterations is constant for every iteration, this works. Okay, so all you do is you look at the incrementer. In this case, because it's going, it's I through, we're going from I equal 1 to I equal n, or maybe like I equal 0 to I equal n. And the first case, we're increasing by 1. That's what's called an, so the counter variable is represented by an arithmetic sequence. An arithmetic sequence is you get the next term by adding a constant. So we're going like 1, 2, I is 1, and then 2, and then 3, and then 4. The j is 1, 3, 5. We're getting the next term by adding 2. So when the incrementer when the counter variable is represented by an arithmetic sequence, it grows like n. So instead of going j goes assigned j plus 2, if we went j is assigned j plus 3, it would be about n over 3. But remember, when we multiply them together, right? When we multiply them together, we're going to drop that dividing by 2. So this is about n squared. This is an n squared algorithm. So if you double, so in this case, the quantity 2n squared is 4n squared. So if you doubled n, the number of iterations would grow by a factor of 4. And I'll have I can't actually write on this. I'll show you what I mean. The doubling, like how many operations, how fast does the number of operations grow? When I open the worksheet up. And here's the other one, and then we're going to go to the worksheet. Look at number 2 there, and what's happening there is j is equal to 2j, and I wonder if I have the. Hold on, students. I probably should have opened this up in downloads. Yes, I'm just going to open this up, right? I think I have this right here. So students, I'm going to open up the same file in here on my computer, and that way I can write on this. In fact, it might be there from the last class. And if this would just open up, I'd be happy. I feel like this PDF annotator gets slower and slower. Okay, so let's just go down to that. Yeah, right here. Yeah, okay. So this is what I want to talk about here. See, this is about, does everyone see this? Do you see this? J equals, you should see the order of growth, and you should see this thing J equals, this thing is not being cooperative with me. I just underlined J is assigned 2 times J. Everyone should see that. Okay, so the outer one, that I plus plus, that's arithmetic. We're increasing, the counter variable increases by 1. It's 1, 2, 3. To get the next value to get the next counter variable, we add by 1. Here, now the inner loop, we multiply by 2. So what is J equal? So J equals, so I'm going to do it in terms of, the first one's 1. So it's 1, 2, 4, 8, and then all the way up to, it gets close to about, n. So in the counter variable is about n, we stop. But so what is this? So I'm going to see if I can write this here. 2 to the 0. Well, 2 is 2 to the first, and 2 to the fourth is 2 squared. 8 is 2 cubed, and it's going to stop at about m iterations where 2 to the m is equal to n. So for some, okay, so when the exponent, when 2 to the m is equal to n, for some n, we stop. Well, what is m equal to? It's equal to the log of n. You don't really have to know a lot about logs. Let me try that one more time. Right, so the number of iterations of the inner loop is about log of n. Because we're skipping a lot, right? We're going from j is 1, and then it's 2, oh, then it's 4, oh, then we skip from 4 to 8. and then we skip from 8 to 16, right? So the number of iterations is that exponent m where 2 to the m is equal to n. So students, you don't have to, even if you're finding this a little bit difficult, one thing I'm just asking you, you can recognize how do we get the next value of the counter variable? We're multiplying by a constant or dividing by a constant. Here, we're adding or subtracting by a constant. So when you're adding or subtracting, it's order n, that's the pattern. And when you're multiplying, or when you get the next term of the counter variable by multiplying or dividing, it's log of n. So the outer loop is about n iterations, and the inner loop is about log n iterations. So you multiply them together, and the order of growth is about n log n. So actually, there's a lot of n log n algorithms in this course, where the order of growth is n log n. We don't really we don't go into a lot of detail about this. I just tell you what it is, okay? So students, let's do the worksheet, and we'll see if we can solve some of these. But we're going to use that rule. Constant number of iterations, constant number of operations for every iteration. And then we'll just look at how the counter variable changes to detect, is it n iterations or log n iterations? A lot of students get it after a while. Okay, so like question 1 there. Suppose we have a one-dimensional interarray with n elements. What's the order of growth for finding the largest integer? So basically what? You need a for loop that, a single for loop that looks at every array element. You have to look at every one. If you skip maybe the largest might be at the end, so you better look at every single one. So it's just, so the incrementer is +1, right? You start at I equals 0, and then you increase it by 1 every time. So it's order n, so the order of growth is n. Now what about, okay, so now you have an n by n array. Here, let me see here if I can. So what would the loop look like for question 2? So it's n rows and n columns. So it's something like this for I, and I equals, let's say 0, I less than n, I plus plus. Okay, and that's what the headers would look like. And then you would actually inspect the array elements and see, oh, is this the one of the largest so far? But you can see here, n iterations, and here, n iterations. So the order of growth would be n times n, or n squared. So are there any questions right now? And then I think the worksheet, we have some, maybe the worksheet will clear it up. But is it okay to look at the worksheet?
Yeah, just a quick question. So just because it's a nested loop, it's n squared, or is it just because it's iterating by one like I plus plus?
But you need both things. You need both. One, you're going n times n, right? So the outer loop has there's n iterations of the outer loop, n iterations of the inner loop, and you get that by, right, because the incrementer is 1. The incrementer is a constant. You're adding a constant to get, in this case, 1. To get the next term of the counter variable, you just add 1. But you're adding a constant, yeah. So each loop in itself is n iterations, and yeah, then you multiply them together. So you need the 2 loops to get n squared.
Thank you.
Okay. So is it okay to look at the worksheet? Okay, now.
Yeah.
Okay. I'm just waiting. I was just going to wait here till someone said something. Yeah, we could be here hours. Yeah, but the video would be really long. The longer the video, the longer it seems to take to process. Okay, so actually I have the work. Okay, so I was going to do it without the salute, but where is okay, I'll just do this. Let's see if I can get rid of the annotations here. Okay, so edit. Okay, the answers are there, but let's just see if we can verify this. So what would, oh, hello. Yes, yeah. So an n by n 2D array has n squared elements. Because you think about it's always the number of rows times the number of columns. So let's say it was like so let's say it was a two-dimensional array with, let's say, like 10 rows and 3 columns per row, then it'd be 30 cells altogether. So it's just the number of rows times the number of columns. In this case, the number of rows is equal to the number of columns. So I think that answered it. Yeah. So your question is your answer. Yeah, you're correct, Kyle. That is correct. Sometimes I think I talk way too much. Okay. Okay. So students, here's just a simple. Okay. So here, let's look at problem 1. And the important thing is to look right here. Okay. So why is it doing that? Stop that. Okay. See, it's a constant number. Well, it's a constant number. So each iteration is one addition. So it's a constant, and all your problems are going to be like this, where the number of operations per iteration is a constant. So all we have to do is look at the header of the for loop. And in this case, this is arithmetic, increased by 1. So, okay, so when you're increasing by a constant, so that's an arithmetic sequence. So is it n, it's order n, right? So it's either n or log n. So in this case, oh, I didn't mean to do that. It's about, when I say n, it's about n. In this case, it is exactly. I mean, if I started IO1, it would be like n minus 1. But okay, so the order of growth is n. N iterations, okay? But now let's look at 2. So you're tripling each time. So remember that's, again, a constant number of iterations. So in this case, it's log base 3. But I don't care what the log is. But let's see, what are we getting in terms of, so first it's, so it starts out of I is 1. So it starts out of 3 to the 0, right? And then we triple it, 3 to the 0, and then we triple it each time. 3 to the first, 3 squared, and so forth. And we stop at, and we stop at 3 to the m, where 3 to the m is about n, right? Because how is that loop going to stop? The loop stops when I is greater than or equal to n. So first I is 1, and then it's 3, and then it's 9. And it stops when it gets to about 3m, where 3m is about n, or you don't have to derive this at all, or m equals log base n. In this case, the log is 3. I don't care what the log is. The only thing, don't remember the way to do this problem, students, but that's basically the idea behind it. It's the exponents that are counting the number of iterations. And that's what we look at. So this is geometric. Geometric meaning we get the next term, we get the next value of I by multiplying by a constant or dividing by a constant. So in that case, it's log of n. So any questions on 1 or 2? So 3 is just kind of like 2. Okay, in this case, we're starting at 2, doesn't matter. It's still pretty much the same. Okay, so here, let's look at 4. And again, in case you're not familiar with that, that means I / equals that's equivalent to I is assigned I divided by 2. We hardly use that in Math 130, but it's kind of like plus equals. Basically, that I / equals 2 is equivalent to I is assigned I divided by 2. So the next value, you get the next value of I by dividing by 2, but we start at n. So we're going backwards. So instead of starting at instead of here we start at I equal to 2, and you double every time, and you stop when I is about n. Here we start at I equal to n, and we divide by 2. We stop when I is 0. And so a student in the last class asked a question, don't you get an infinite loop? No, because remember, when I is less than 2, like eventually I is 0. So let's say if I is 1, 1 divided by 2 is 0 in Java, right? We're talking about integer division, not if it was floating point, it would be different. But I is an integer, 2 is an integer. Yeah, so 1 divided by 2 gives you 0. So 4 and 3 are really pretty similar, but in this case, we get the next term. Again, this is what tells you. This is the only thing you need to look at, students. Oh, it's geometric. We're getting the next term by or dividing by a constant or multiplying by a constant. So log of n. Okay. So let's look at this case. Okay, here's one. So a nested loop. So arithmetic, and we're decreasing by a constant. So once again, it's each one is about order n. The middle one, because we're subtracting 2, it's about n over 2 iterations. But remember, we drop all the constants, so it's really like n squared over 2. But remember, we drop that factor of 1/2. All we care about is that highest order term. So it's not exact, but all we care about is the highest order term. So that's why, again, we just multiply these together, n and n. Okay, so let's try a couple more. Okay, here's one. Whoa. Students, this is probably one of the most exciting things we've done all day long. Okay, so triple loop. Have we ever seen a triple loop before? Okay, so, but look at this. Increase by a constant, multiplied by a constant, multiplied by 1/2 or divide by 1/2. So it's n times n. And we would write the answer like that. Any questions on 6? Again, you just look at the pattern and you just multiply. N log n. You multiply. That's how many iterations. The innermost loop is about log of n. And then if we take this loop here, it's n over 3 iterations times log of n. And then you multiply that whole thing by n. So if you see the pattern, these problems really aren't hard at all. If you just ignore all the stuff you don't need and just cut right to the important part as far as solving the problem. Okay, so I am going to do 7 and 8 next time. And that'll maybe be a more advanced problem for our quiz. But here, what's a little bit different, I'll just show you. It's really not that hard. It's instead of the incrementer telling us how many iterations, it's this it's that Boolean, it's not I less than n anymore. It's I less than math square root of n or I less than n squared. And that's what's telling us the number of iterations. So that's why 7, it's really, you only get a square root. The number of iterations is about square root of n.
So questions 1 through 6 would be on the quiz, but 7 and 8 would be for next time.
And I'll put that online so you know what to study.
Thank you.
Yeah, so that'll be next time. So let's just do a few of these. And 9, this would be the last one, I think. 9. And again, all you have to look at is the dominant term. What is the dominant term? Like n squared grows a lot faster than 1, right? So for large n, isn't n squared a lot greater than 1? I mean, 100, let's say if n is 100 squared is a lot bigger. When you just keep putting in, the bigger the n, the greater than 1. So for large n, we really don't care about that plus 1. And then, again, this is a strange expression, b. You just look at, well, n to the 4th grows a lot. For large n to the 4th is much bigger than n cubed or n. So you just look at the highest order term. And students, we don't write the coefficient. So if it's a polynomial, you just look at the highest order degree. Okay, so C is a little bit interesting because, okay, which is, for very large n, what's dominant? And what happens is 2 to the n goes to 0. Like 2 over 1,000,000 is a super small. Remember, the larger the number that you divide by, the smaller the number. So here's the graph of like 2 over n is. So those of you taking calculus, it's got a horizontal asymptote of 0. But yeah, the bigger the n is, the closer 2 over n gets to 0, where 1 just stays constant. So the dominant term here is 0. I mean, I'm sorry, is 1, not 0. There's no 0. The dominant term there is 1. So for large, basically what I'm saying is for very, very large n, 1 over 2 plus n behaves like 1. So let's say, I'm sorry, so if actually I graph that whole function, what would it look like? We get closer and closer to the line y equals 1. So 1 plus 2n and the function 1 over 2 plus n and the function 1 are almost identical for super large values of n. So we say the order of growth is 1, because that's what order of growth tells us. How is this behaving for very, very large n? And the same thing for d. You just multiply all those terms out, and well, you can actually apply the limit. You probably learned that in your algebra class, that you may have forgotten. Or you can just multiply this all out. You get all these terms with right, and so you get all those terms where when the n is in the denominator, it goes to 0. So once again, this function here or this expression here, if you graphed it for very, very large values of n, it looks like, this constant line y equals 1. So the order of growth is 1. And then we're going to skip. Maybe we'll do the last two the next time. These are really, if I was in class, we might talk about f. I have the solution right there. The order of growth, it turns out if you actually, log of 2n is very similar to log of n for very large values of n. We're just going to skip that, students. Maybe we'll talk about, maybe it'll be on another quiz. But basically what it's saying is that for large values of n log n is much, for large n, n log n is much greater than n. And you can, maybe I'll come up with a graph for that. But I just wanted to show you one other thing, students, before we go. So we keep talking about this order of growth. And why is it? Let's say the order of growth is, okay, and I'll tell you, so I'll tell you which problems to study. For the quiz is like 1 through 6 and problem 9. But I'll put that up later tonight. I just wanted to show you one last thing, students. So let's say we have an order n squared algorithm. So it's growing like n squared. Now what happens is, let's say, so data size equals n. Let's say like an integer in your sorting. So let's assume the order of growth, order of growth equals n squared. So that's an assumption. So let's say some algorithm and the order of growth is n squared. So now let's say we double the data size, double it. So the data size is 2n. So in this case, the order of growth, I just had a hard time expanding. Oh, look at this, is equal, and now we're going to put the 2n in the square, right? Isn't that, if we distribute the exponent, the log of the exponent is 2 squared times n squared, and that's 4n squared. So if you double the data size, right, so let's say we go from 100 integers to 200 integers, like we're doubling the data size, the number of operations goes from n squared to 4n squared. Oh, so it's going to take 4 times, so if the algorithm is n squared and you double your data size, it's going to take 4 times as long to run. So that's not good. Right, so we don't want it. So when we double the data size, we don't want it to take 4 times as long to. So let's say the algorithm takes, let's say it takes an hour to run for something of size 100, and we double it to 200. Oh, now it's going to take 4 hours. That's a long time. I mean, our project is due in an hour and a half. What are we going to do? Oh, I guess we'll get enough then. Okay, so but yeah, so basically this is what that order of growth, you just double n and see what happens. And let's say if it was an n cubed, assume, I'll stop talking. I kind of like math students, so I guess I talk about this stuff. And you're not tested. Let's say order of growth is n cubed. So let's say you double the data size. You go from, so for size n, it's the number of operations is n cubed. Data size, let's say we double the data size. Oh, wow. 2n cubed. You know what? You're going to get 8n cubed. Wow. So if you don't, so if it's an order, so if it's an n cubed, let's say the number of operations is like n cubed. Let's say n is like 100. We're trying to sort 100 numbers, and it takes n cubed operations to sort these 100 numbers. And you double the data size. Oh, now it's going to take 8 times as long. Oh, that's really bad. So we don't like n squared or n cubed algorithms. Oh, you are, Kyle? Oh God, I felt bad for you. I'm still learning all the names. I never see you people. I feel bad about that. Okay, so anyway, okay,
No, I'm not in your math 250. I've just meant I'm in math 250.
Oh,
and
math 250. Okay, so now I don't feel so bad. Now I don't feel so bad that I don't remember you being in math 250. Okay.
Okay.
Oh, you watched. Oh, so you watched math? I think
So I'm
yeah.
able to watch your lectures too as well.
Okay. I hope they're okay. I hope they're not too bad, but I try my best. Okay. It's totally, I haven't done 250 in this this online environment, so it's all new to me. This math 140 I have. Okay, so that's why we study order of growth. You double the data size. Oh, how much longer is it going to take for your program to run? But if it's just order n, no, double it just takes twice as long. That's what we like, linear. So students, your quiz. First of all, you have the new assignment. You have if I think you need more time, I'll give it to you. But just try it as soon as you can. The quiz will be you'll write a couple of constructors where you use the keyword this to call a constructor in the same class. That's what we did last time. But I'll post when I post the announcement for the quiz. I'll post the links to the files. And even this assignment, that person class has some. Maybe it's the same person class. And then what we did tonight. I'll give you some I'll give you problems like this. So you'll expect problems like 1 through 6. And what I found is people really get it or they just don't get it at all. Problems like 1 through 6 where you have these nested loops. And I think what I'll do is I'll put up an old quiz too. And then maybe a problem like number 9. So any questions, students? Is it okay to stop sharing? No objections? I gotta share again. I'm going to stop the recording.